So our use case, or we searched for a sensor model language. We had several measurement stations deployed with several weather sensors attached to. And we saw were in situ sensors. So we had a SWE infrastructure in place, so a sensor observation service, and we used WaterML to describe our observations. And yeah, we needed a very detailed sensor description for our sensors because we wanted to harvest sensor information, harvest the provenance information out of these descriptions. So we started to build a profile for SensorML, and we also later wanted to map this description to the semantic sensor network ontology. But this was a real difficult task, and we went over to develop our own model because some attributes or elements of the NO couldn't be expressed in SensorML. For example, a platform is expressed differently in SensorML. It is understood as a process. We wanted to define it as not as a process, but as a platform. So we had a closer look to what a sensor is, and we identified two core parts of what a sensor is: a static part and a dynamic part. And the static part is that for a sensor model, often there is provided a sensor attribute sheet where all the information, what a sensor model is, or the measurement capabilities are described, or what a sensor observes. In this example, it observes wind direction, rainfall on the others. And the dynamic module focuses more on time and space related and the deployment of the sensor, so that you can deploy and redeploy a sensor, or where a certain sensor of a certain model is. We needed a name for this model, and we call it the Starfish Fungus language, after an interesting creature that we found in front of our research institute in Australia. And it is modularized. It consists of two core modules, the static and the dynamic module, plus an additional one. It reuses and reinterprets concepts of XSNO and SensorML. It aligns to semantics and interfaces of ONM, or the SWE environment. Not as SensorML. It is more restrictive and hard-typed, and we performed the Pareto principle to not to describe every single special type of sensors, but we can describe most of the sensors. We also have extension points, and the technical part is done. So we created a UML model and converted it to an XML schema using the Hollow World environment, and converted it with Full. So you see the core parts of StarFL. In the top, there are the two key elements of the static module, so sensor characteristic and sensor procedure. Sensor characteristic represents all the device-related types of the sensor model, so physical properties like height or weight of sensor, or operational properties like survival range, or things like that. And the sensing procedure encapsulates exactly one observed property and the belonging measurement capabilities or unit of measures. The dynamic module, or the core elements of the dynamic module, are sense and sensing. So sensor, or a sensor element, is or represents a sensor that can be deployed in the field. it links to its belonging characteristics. So for one model, the characteristic must only describe once and made accessible, and then we can, with each sensor of this model, we can link to the sensor characteristic. And it uses the same pattern as sensor characteristic to sensor sensing procedure. It senses 1 to n sensings that themselves link to exactly one or their belonging sensing procedure. You can see an example of a static module and dynamic module. We applied to Vaisala WXT520 weather sensor. So in this case, the static module models that Vaisala WXT520 provides two sensing procedures, wind speed and temperature. And the sensor instance of this Vaisala with serial number 11111 senses the belonging sensings, wind speed and temperature. The static module, or the information for the static module, is provided by the sensor vendor, and the dynamic module is provided by the sensor operator. So if a user wants to create a sensor description, he has to perform mainly two steps. The first step is to find the static description on the web for the particular sensor model he or she wants to describe. And if it was available on the World Wide Web, that could be either on the manufacturer's homepage next to the PDF sheet of a sensor, or even in a centralized sensor catalog. Most of the work is done, and he could step to step 2. And if it was not available, the user has to create the static description by himself. And that is mainly translating the information that is in a sensor attribute sheet into an XML form. So the sensor characteristic and the sensing procedures that are aggregated by a sensor characteristic. So in this example, we have a Sensirion SHT75 sensor with the manufacturer Sensirion AG. The model is SHT75, and it provides two sensing procedures, relative humidity or temperature. After that is done, you could continue with the dynamic description. So the first step is to extract the sensor instance and link to the static description. Here's an XML except of this. So start our sensor with a certain GML ID, a serial number, and 39, and the link to the characteristics of the characteristic XML file, and the aggregated sensing elements with links to the belonging sensing procedure. Step 2 is if there is a platform available. In this example, we have an UAV, the helicopter. The user has to describe the platform. You can see the UML model with the platform, so you can describe whether it's mobile or the operator. And after that is done, the user has to link the platform and mount the sensor by a sensor deployment. The sensor deployment element encapsulates all dynamic data, so where a sensor is deployed, when it has been deployed, or who has deployed the sensor, or what restrictions were followed to deploy the sensor. So we have in the upper picture the SHT75 with the serial number 23002. And this is deployed during the time interval T1 to T2 on the helicopter platform, and after that removed. And the second sensor with the serial number 23003 is deployed during another time interval. We can also, or this is a mobile platform, and we also have static platforms, or a sensor doesn't even need a platform to be deployed, so it could be deployed by its own. The last step is if there are calibration information available to describe the calibration information. The future steps, the current steps, we are busy to build RESTful services to manage static and dynamic sensor descriptions. And here we want to integrate the model now into the sensor bus and provide mapping mechanisms to XML and to SNO, and of course apply and test it in certain projects that are warning client, governance, recalibration, redeployment, and sensor plug and play related. Yeah, and we have to solve some open issues. Thank you very much.
Thank you very much. One short question. So I have one question. So since you're developing a new language, you mentioned briefly about other similar metadata language out there. Do you think it's your responsibility to make sure that at least yours complement to others, or you meant to replace others?
We mainly developed it first for our use case.
For your use case?
Yeah, for our use case, and Simons has also presented it to the OGC, and yeah, it's an all. So
you want the community to justify it?
Yeah, and yeah, maybe with the development of SensorNow 2.0 is going on at the moment. So maybe we could involve to the development of SensorNow 2.0.
Yeah, fair enough. Thank you.
Okay. Hello everyone. I'm Jung from National Taiwan University, and this is our group. Today I will give the talk is about we want to build up a platform that we use the ontology technology and the multi-agent systems to management and integrate multiple sensor data. Okay, so first, thanks to OGC, they initiated the SWE standards. So we have the SOS, Sensor Observation Service, SAS, or SML, or ONM models. So these standards make the sensor data to be published in the web service, so we can access these different kinds of web service over the web. And this study was focused on the SOS. What is SOS? But I think everyone knows what is SOS. SOS provides a standard operation to access the sensor's data. So the operation includes a get capability, describe sensors, or get observations. And this study was focused on the get capability operation. So this is an example from OGC. And we can send a get capability request to the SOS, so then we can get the response in XML. And that includes the sensor information that include observe time, observe location, observe procedure, or observe property. And moreover, we want to focus on the observe property because it's the most flexible and the most semantic heterogeneous. So we want to focus one because we can use the different terms or different language, or use the URI, Unified Resource Identifier, to describe what phenomenon the sensor observed. So for example, we can use the different terms to describe the observed properties. Like for example, we can use the river, or use the lake, use the stream, use the creek, or different language to describe the phenomenon in observed properties. So many different terms, how do we know they are similar or different? Or even though we human knows the different or similar, but how do we make the machine to understand the thematic difference or thematic similarities? So we want to handle this part. So how to integrate and share the different SOAs in different semantics, and how to overcome the semantic heterogeneity is our study. So we propose a web portal. It's like a registry over the web. So we can register this kind of these SOAs into this web portal. We call this web portal as MACOSI, multi-agent knowledge-oriented cyber infrastructure. So this is just like a register, and the web service provider can register their SOAs into our registry. And we use the two technology. One is ontology for the semantic interoperability, and the other one is use multi-agent system to simplify the complicated task when we develop the system. Okay, so the first one, what is ontology? And ontology is a conceptual model that we can formally define the definition of the concept and the relationship between this concept. You can imagine that the ontology is like a knowledge map. Everything is interconnected. And there's a node. The node represents the concept or the individual that belongs to the concept. For example, there's an air pollution concept, and there's another concept for the wind. And between air pollution and the wind concept, there has a relationship to link together. For example, stronger wind, because stronger wind may influence the affected area of air pollution. So these two concepts maybe have a specified relationship between each other. So we can use the ontology to link together. And the other one, for example, the precipitation maybe have another relationship to the wind concept. And the SOS can be think individual that belong to the one concept. So everything will be connected and be meaningful in the ontology. So and moreover, we can use some standards like the OWL, the Web Ontology language, to describe this kind of ontology in XML file. So machine can know the definition and the relationship between between the concept. So the machine can understand and to help us to query in ontology or reason new knowledge in ontologies. So this is ontology, and we build out some ontologies. So SOS ontology is our core one, and we follow the OAM model to build out this ontology. So SOS may have a URL, and may have the name, and may have several observation offerings. And each observation offering may have several observations that measured by different sensors. And each observation and the observation offering and observation may have connect to different concepts, like the observe time, or observe location, or feature of interest. This concept is defined in different ontology. And also, they will have a lot of concepts like observed properties. So observed property, we didn't follow any standards for the observed properties, but we follow the standard like the ISO time for the time ontology and OGC simple feature specification for the location ontology. But we define our ontology by ourselves for the observed property ontology because it's too flexible. So we cannot follow. We didn't follow any standards for that. So under the observed property ontology, we can define the different concepts like the wind, air, or the water. Under this concept, we can have the sub-concept like air pollution under the air concept, or the PM over the carbon dioxide. So we can use ontology to define the definition of the concept and relationship between them. And besides the ontology, we also use the multi-agent system, right? So here we use the different multi-agents. So this is the MACOSI, the application web portal we developed. And we use several agents. The agents is just like the software programming model. It's like the module. So we can define a different function to this module or to the agent. So the first one is safeguard agent. So the main job for the safeguard agent is to check authority of the user. So if the user has authority to register their web service in our web portal, so the safeguard agent will check that. And then the safeguard agent will go to the directory facilitator to looking for if there are any available agents to do the following jobs. So if a user agent is available in the directory facilitator, so the safeguard agent will find this user agent to do the following job, such as monitoring users' activities, or help the user to register their SOS into our web portal, or help the user to search any SOS in our web portal. So this is a user agent, and the user agent will call the service agent. The service agent main job is to send a get capability request to the SOS service, and then they will get all the response from SOS and show this information in the macOS. And this is the main job for the service agent. And the other one is ontology agent. Ontology agent will get all the information in ontology and show the concept or the relationship in the macOS, the web portal. So we adopt the several different kinds of agents: the safeguard agent, user agent, service agent, and ontology agent to build out the macOS web portal. So this is my favorite part. So this is our portal, web portal. You can go to the website www.macos.com, but we have to apologize first. And right now we just only have a Chinese version, but in English version will develop in near future. So yeah. So this is macOS. So the web service provider can go to macOS and to register their SOS into the macOS. So the provider needs to input some metadata of this service. So like the name, like the URL, like the type, and additionally we have some business model or business value in our web portal because we think the data in our country, we have to buy the data. It's not like the United States, we can free download the data, but in our country, we have to pay the money to buy the data. So here we just provide a business model there. So other user can pay the money to buy your data. That will be charged daily, weekly, monthly, or yearly to charge you to use the web service. And also we provide a trial period for the user to free use this web service. But this business model is not our focus today, so we skip it. And moreover, we can give some descriptions of this web service and to upload some screenshots in the web portal to let other people to know about the SOS web service. And then remember our service agent. The service agent will get the URL and to send the request, get capability request to the SOS service and get a response. So this is all the get capability response of the SOS service. And you can see here we provide we show the observation offerings, procedure, coordinate systems, and observed property. And the user can manually annotate this observed property to our concept in ontology. How to do that? When the user clicks this observed property, there's another pop-up window. There's another window pop-up, and this one is ontology agent to help get all the concepts into the ontology, into the macro system. And the user can manually check which concept is best represent the observed property. So user can choose. And of course, the user can multi-choose the different concepts for the observed properties. So this is what we do to manually annotate the observed property to the unified concept in ontologies. So once the provider registers their SOS in macOS, So the SOS will show in the web portal. So the other user, like the web service consumer, can discover the SOS by browsing the concept in our website. So this concept is from ontology. So user can choose maybe the air quality and choose the carbon dioxide to discover what SOS is belonging to this concept. And moreover, because everything is defined in ontology, so we can use some advanced semantic way to query this kind of SOS. So we use SWE, semantic web rule language, that is use rules to discover the SOS web service. So, for example, we can define a new concept, use the rule. This is for the severe carbon oxide concept, and we can define this concept that if the SOS, the observed value is more than 30 ppm, so we can call this SOS is a severe carbon oxide. So we can use a different way to query the ontology in like this one. So in conclusion, we just developed a web portal. It's like a register for the SOS, so the web service provider can register their SOS into the web portal, and we use two technologies, ontologies and multi-agent systems. And in the future, we want to involve more geospatial web service like the WMS, Web Mapping Service, WFS, Web Feature Service, and WPS, Web Processing Service for the model or functions. So this different geospatial web service will also use the same idea to reduce into the Makosi. And also, we want to link to the linked data because we want to let the Makosi become a node in linked data cloud. So linked data is a project that want to interconnect the web database in a semantic way. So everything will be connected in a linked data project. So I think the next speaker will go detail about the linked data. And for the future, we want to be a node in the linked data. So everything, if other user want to link the resource like the web service in Makosi, they can link together. So this is our future want to do. So that's it. Thank you.
Thank you. One quick question, me? I wonder if you keep tracking the status and the quality of each service that you're providing. So that you have like, through web service, there's like internet connection quality and the data quality. Do you report that to the users as well? We have procedure to do that. Yeah, to monitor the web service. If the web service is shut down, there will be a red light. Right, so you report that.
Yeah.
Okay, yeah, I'll have more questions in the chat.
Okay, thank you.
Let's move on.
Hello, I'm Liang Yu from University of Illinois. Glad to present you a piece of our research, which is about using linked data in a heterogeneous sensor web. We have identified some challenges, experiments, and learned some lessons which we want to show these people. So here are the contents we are going to cover. So let's start with introducing the motivation. Interoperability has been a grand challenge for sensor web. Consider that nowadays we can get more and more useful sensor data, but there is still a need to integrate different sensor data, city sensing and other geospatial data. For example, consider this simple query. Can you give me all the river change height values from orchids in Illinois between this period? USGS provides us a RESTful service which we can use to query this data. But to do that, we have to do multiple queries and switch back and forth between different services, and we still need to do a lot of transformation and processing. So the reality is the sensor web is heterogeneous. Data are accessible via different protocols and in different formats. And usually there is no, or a few semantics attached to the data, and there is no links between different data. So we think the linked data might be the potential solution for this kind of problem because of these principles, which are URI naming system, HTTP protocol, and RDF. All of these can solve both the syntactic and the semantic issues. And also, it emphasizes on making links. So the final goal is that we want to build up a linked sensor web. So in our research, we wanted to incorporate data from different agencies for the emergency management and environmental management purpose. We got sensor data from COSI and the USGS. We got even data from NOAA, which are basically hail, tornado, or wind. We got earthquake stream from SSA, that data stream API. We think people might be interested in how this environmental events data can be used for to evaluate the impact for public facilities. So we got data from Open Government Data Initiative. This is the website. They provide data in OData, so we can see there are a lot of heterogeneities here. We got different data sets in KML, WaterML, and in shape files. They can be accessed by REST service or SOAP service, or even a downloadable link. So we use linked data to integrate those data and reserve them to the sensor web community. Here is a simplified view of using linked data for the query we mentioned before to get all the observations from the sensors in Illinois. It can be done by this simplified way. We look at this data map, national map, and we find out a link to the Illinois state, and then another link to all the sensors in Illinois. And for each of the sensors, we can get a link to all the observations generated by this sensor. The key challenges for this work is two parts: data publishing and consuming. First challenge for data publishing is how to add semantics. What kind of semantics we can use? So we propose to reuse the existing ontologies rather than developing new ones. And how to discover the potential links. For this problem, we propose to use geometric analysis to discover links between spatial data. The first challenge for the data consuming is how to serve this data. We have a lot of SOS, but we propose to use linked data API to serve this SOS. It has many advantages we will mention later. And we think problems tracking is very important for people who want to evaluate and validate this data. Here is the workflow. So we can see the raw data is on the left, is converted to XML. If some of the data are already in XML, this step is unnecessary. And then we use the styles XSLT and ontology to process this XML. In this step, we do multiple things, such as annotating semantics and making outgoing links and checking problems. Then we got linked data. This linked data is not enough. We use geometric analysis to discover spatial links. Then we get more linked data, and we use the linked data API tool to reserve those data to sensor observation service. So we will address those four challenges one by one. First one is republishing. we have mentioned we use the XML and the XSLT style sheet to process the data. We do different annotations to process the data. First is semantic annotation, which is to add semantics from ontology to the data. And we make outgoing links. DBpedia has a lot of web pages describing the spatial features such as states, counties. So by linking to them, we can get more data and we track problems. The reason we use the style sheet and the XML is they are language independent. They are reusable. We don't have to change our program to add a new data source. Also, we can share this style sheet once it's developed. We can share with others. Anyone can use it. So there is the example shows the process of transforming the lesson map, which is in the shapefile, to the state map in RDF. It's firstly transformed to KML by using this tool. Then in the style sheet, we can see a lot different boxes. Red one is the RDF type annotation, use the semantics for ontology. The green one is the provenance tracking. In this case, it basically says this data is from this link. You can download raw data from this link. And outgoing links, in this case, it means this state, Illinois state. You can link this to the DBpedia. There you can find more data. So let's talk about the ontologies. We use multiple ontologies here. The major two ontologies are SWE ontology, semantic web for Earth and environmental terminology. It provides us a lot of domain ontologies, ontologies and the concepts. Another one is the W3C semantic sensor network ontology. We also use W3C GeoOntology and Tag ontology. We use the OGC GeoSparkle, which is now listed here. This picture shows just a small portion of the concept. The reason we want to show it here is to show that we need to integrate those ontologies so that we can use the semantics from multiple ontologies to describe a single thing. This is the process of discovering spatial links. There was a similar work done by researchers from Free University in Germany. The difference we made here is we use the geometric analysis rather than text analysis, which is used by them. So we use GeoTools, Java library to read this to RDF datasets and extract spatial information from the datasets, and then after geometric analysis, we got more links based on the topological relations. Here is the example following the former example. So we already got state map in RDF. In the same way, you can get synthesized in RDF. This geometric analysis will read coordinates information from the two datasets and gives as a result, it says this state is in Illinois. The provenance tracking. Provenance is about where the data come from, how were they processed. For this purpose, we use open provenance model. So here's a simple example. We have sensor data, we have observation data. Both of them have provenance pointing to the agencies that provide us those data. It uses the predicates from OPM, and also there is provenance between the observation and sensor. For this provenance, we can use either the SSN ontology or the OPM ontology. Doesn't matter because ontologies can be aligned, map or match in an easy way. I want to show the services we developed. We provide a sensor observation service by using the linked data API. Linked data API is very flexible as semantic query language is Sparkle, but it's much easier to use. Here are the 5 different types of SOS services we provide. For example, to query the feature of interest, here we can query the watershed to query a single sensor connection of sensor size, or a single observation or connection of observations. Here is the query result. So this query can be accessed from that URL. It returns all the sensor size in Illinois State. From the result, you can see there are a lot of outgoing links. It has a link to the semantic defined in Web Ontology. It has a link to the sensor network. It has a link to the data stream it generates. It has a link to the agency which provides this data. It has links to all the spatial features, states, county, and watershed, which contain this sensor. So we can use this to explore the whole data set, explore the whole linked sensor web. So an example is given by using the World Wide Telescope. We see this. We saw this yesterday. It has Excel plugin, so we can provide data. So, excuse me, I haven't explained this. This data is in JSON, so we can easily change the format to other, for example, XML, CSV. So in this visualization, we use the CSV and use the Excel plugin to visualize this data. It is animation because this data is streaming data. So the URL we can see is very long because we have a lot of parameters to specify the time and observe the property. Then we got this animation. It's a snapshot. So let's conclude our work. We are proposing to create a linked sensor web solution for integrating heterogeneous sensor web, sensor data sources, and geospatial data. We propose best practice using the WCVC, SSM ontology, as well as other ontologies. We propose to use the geometric analysis to discover more links. We propose to use the linked data API to provide SOS service. All the APIs can be found in this web page. We use the OPM to track the progress. In future work, first, we want to improve the geo-streaming capability in current implementation. Also, we want to improve the performance. Performance is always the issue for all the RDF-based application. We want to help the search engines to make use of this, discover and make use of this linked data. We want to create an end-to-end performance management system for this application. This work thanks to the software research and I had the UIC. Thank you for
Any questions? Go ahead.
Yeah, that was very interesting. Thank you. I'm curious how your approach would work with data that change dynamically frequently, because you have a process that you have to go through from a static data set to make it a linked data set. How would the impact of that original static data set if it changed frequently?
We haven't shown architecture, which is in our paper, but we haven't shown it here. So in this architecture, we have data accessing, we call that data fetching layer. So the data we integrated are not only static data. For example, the USGS provides us streaming data, which is real time. So when our intuition is that in this architecture, when user wants some data, he sends us a link, send us a request, and we go there and fetch the data back and make it linked data, then serve back. So because the web data is immense, we cannot cache all the data in our site. So we propose to use this dynamic way to do that.
So you do that on demand.
Yeah.
Yeah, let's hold on any more thoughts on this and then talk to the coffee house.
So I'm Janet Fredericks, and I'm from the Witzel Oceanographic Institution. I manage and I'm systems programmer for the Martha's Vineyard Coastal Observatory. It's a cabled observatory that serves real-time data both to the world and to a series of projects each year that come and plug in and do kind of innovative things. So my main purpose is to take care of our scientists and make sure they understand the data. And things were going fine, but people started asking for the data, and I forgot that has kind of changed slightly.
Just forward on the far bottom right.
Thank you. From my perspective, I'm the data provider, and the nightmare is U.S. agency, the National Data Buoy Center says, please install the modem kit and put it in your data in this format. The NODC wants that format. OOI says, oh, we'll take your data, but install JSON. And the modelers want me to install a thread server. So with that comes the luggage of making sure everything works with my new operating system and making sure anything that I do in the field, our operators do in the field, gets passed on to those people. It's a big responsibility when you start moving away from your local little world into this other world. And someone asked me earlier, why would I do that? And I think it's a good citizen thing, and not only that, funding agencies are now saying, you have to put your data out there. And so I look at myself in Dr. Lang's world as the dark data. He refers to the dark data. We have really useful data. We're making wind measurements at 20 hertz. People are interested. I don't know who they are, and it's not my responsibility to take care of that data for them, but I'm willing to offer it. So what I'm looking forward to, and also these people also have the same inverted nightmare, trying to deal with me and everyone else. And now we're going and moving our data and everything we know about it through whomever we send it to these other agencies, and it gets further and further removed from me and the people who work on my data. So that's kind of what my talk is about. So I'm looking at pretty much that end of this picture in my talk today. I hope a lot of people are working on this cloud concept, getting QC algorithms, converters, so I can put out data in a standardized format, and I've chosen OGC sensor web enablement. I feel it enables interdisciplinary research because it talks about sensors, sensor-based geospatial, that could be almost any type of Earth observation, and that's what I'm dealing with. So I'm assuming people are working on these converters and QC algorithms and the tools that'll kind of move me into only having to deal with my local way of getting data out, and then maybe one other standard, which I've chosen to be OGC sensor web enablement. And fortunately, I have a project called Q2O, and I now have NDVC willing to ingest these data in standardized format. So that offers an additional value to me because they have 24/7 operators doing QC. But I still have that responsibility to pass on the information about what's good or bad about these data. So in my world, I have sensors. They're on the network. I have operating in real time, and I'm logging and processing these data, and I provide them through a web service. So there's things going on between the sensor, there's QC processing, and there's derived properties. So this project Q2O came from a lot of different projects, brought me to this point in setting up this project. I was working on Quartot, and in that group, it's quality assurance for real-time oceanographic data. They had already worked to develop the QC tests. They're already defined, but they're not dealing with interoperability. There's the MMI, Marine Metadata Interoperability Project, worked on developing vocabulary tools to develop those on top of those OWL, converting their vocabularies into OWL and registering them on the net. and providing guides on developing vocabularies. And OGC, of course, we've heard about, and there are a number of other groups enabling you to easily put OGC services on my website. But I wanted to go a step farther and talk about quality assessment and ability to do dynamic quality assessment. So once we were funded, we had community meetings. Each parameter we'd have 2 to 3 meetings, and they'd range usually about 25 people. They range from 8 to 70, but usually about 25 people. We had domain experts who knew about what was needed in their domain. We had sensor manufacturers, marine operators, and IT specialists. You can see Mike Botts in the picture. He's the author of SensorML, and Carlos Rueda is to the right of me, and he's my co-author, and he's from Monterey Bay Aquarium Research Institute. So from these meetings, we came up with the content specifications and the model that I'm going to talk about in 10 minutes. We have the SOS service, harvest SensorML, and also harvest the data, and puts out the data and get observations in O&M, and the sensor descriptions and the system descriptions and the platform descriptions in described sensor. And these SensorML files have been infused with URLs, which can be referenced. So the client can resolve the URLs, and the SensorML references those URLs that are registered on the web. So here's an example where I took one of the properties in this case and have a URL. That's the MMI SWE is an ontology repository registry. That was how we created the definitions. And one of the things that we worked on with the domain specialists was to really describe it. Don't just say pressure is pressure, and that's the end of it. But include a complete definition and reference authoritative references. So things that people in your domain are really going to understand. In this case, it's the IHR, and or it could be a book or someplace that's authoritative and definitive. This is how we derive that property. And in the URL, we can also have a process. So you can have a process that has input, output, and parameters, but you'll point to an authoritative reference where it shows you how you got that derived property. In this case, those URLs, since they're registered, and in OWL, you can use them to build the ontologies that were referred to earlier. So in this case, you can say my QC flag is the same as someone else's QC flag, even though we call them something different and they have different values. So you can use code space to get over the problem that my good data has a 0 flag and someone else's has a 3. So by registering those terms, you can get around those problems. So this was the model. So aside from infusing it with the URLs, so you can build ontologies, we came up with a set of 5 role-based categories of SensorML. 2 are related to the sensor and the deployment, and 2 are related to the processing. The OEM file is the original equipment manufacturer model and deals specifically with things that a manufacturer can tell you. So again, like Chris mentioned, you kind of have this static view of what a sensor is. You have accuracies that are specific to the sensor, things that they know about it, moving beyond an HTML file, which is great. Now we can get manuals on our phone, but go a step farther and have these descriptions in SensorML or some standards-based encodings. Then you take those, and from those you can build the information about your setup and your setup, your configuration, your deployment, and your event histories. What happened? I went out and cleaned the sensor faces. And going down to these details is very important. It's difficult, but it's very important. And then we have a QC flag category for processing. So I send it to the NDVC and they can look for my QC flags. Instead of throwing out data that might be a tsunami, they get it, there's an alert, and either I know I have to go out and clean the sensor faces, or they know they have an event to deal with, and so do I. And then again, as I mentioned before, processing so that people know how you got your derived property. And through this model, one can find out that this wave height was derived from a Doppler sensor, not a buoy, that this wave height was based on frequencies or sampling frequencies versus how long of a frequency period you had. You can decide if it's good for your application. I don't have time to go through this, but so we need to work on a better sensor ML editor. We need sensor registries, as we heard earlier. We need to promote fully describing process lineage and sensor descriptions. We need to work with domain experts to create meaningful vocabularies, include authoritative references, and to register these so they can be used to build ontologies. Q20.hui.edu is the where you can find information about the project, and node/node/129 shows you our Waves implementation, and I think that's it. That's the only way we're going to have any confidence in our observing systems, is if we can somehow assess the data that we're looking, that we discover. All right?
Thanks, Gina.
Thank you. Hi, my name is Alain. I'm here again. Today I'm going to talk about analyzing performance of XML data value solution for SOS applications. The motivation for our work is that, as I was telling yesterday, SOS applications are common on web and desktop environment, and it's just a matter of time that they become common on mobile devices too. So, but still we have a problem, is that the SOS protocol based on schemas are very big, are very large. The structure of the XML message that are exchanged between clients and server are very complex. Actually, they have the version 1.0 have more than 700 types, and this type are distributed over more than 80 schema files. Then, when we are developing XML processing code, we have two choices. We can use low-level APIs like DOM or SAGS, or we can use an XML data binding tool. If we use low-level API, we have a problem, especially if we are dealing with very large schemas. It's like we have to write a large amount of code that is potentially error-prone because you have to do all the time conversions by hand. You have to be careful with all the nesting of the elements and levels, etc. It's very complicated task. I have done it myself, so I don't recommend it to anybody. So, what is advised usually is using an XML data binding tool, but the problem is that the generated code produced by the tool usually needs more computational resources. That's why some developers prefer to write the code by hand. So, in this context, our objective was to analyze to what extent the use of XML data binding solution was a problem when they were applied to SOS applications. We are considering here two platforms. We are considering Windows 7 and Android. In this platform, we try to measure execution speed, memory consumption, and size of generated code. For our experimental setup, we use 4 datasets of real SOS data that was gathered from a set of sensors. We have a dataset for capabilities file, another for sensor descriptions, and 2 others for observations and measurements files. We use 4 data binding tools. All of them were capable of generating code that could be executed on PCs, and 2 of them generate code for mobile. And we use 2 hardware platforms, an HTC Desire Android phone and Windows 7 PC. Here we have the execution times in the mobile scenario and the PC scenario for the capabilities files. Here, we can see that well, we cannot actually see it if you don't look it close, very close, that the execution times for the mobile phones were about 60 times slower than for the personal computer. Generally, for the rest of the data sets, more or less the difference between times were about the same. And looking at the actual values of the execution times, we can say that XML processing code does not seem to be a bottleneck for P6. We can actually process very large file of several megabytes in a few milliseconds. And it's not the same for the mobile scenario. To process a 3 megabytes file in the mobile, we need around 10 seconds, which is a very large time, especially if we have a user waiting for the information to be shown. Then the high processing time for mobile raises the question if the current SOS protocols are appropriate to be implemented in mobile devices. We can maybe try to use another format that is less verbose than XML, like JSON or some form of binary XML or anything similar. For the rest of the data sets, the sensor description files were very small, so the execution time were not high. In the case of observations and measurements files, these were very big. Observation files used to contain about 7 times more observation values than measurements files of approximately the same size. As a consequence, we recommend to use the former in mobile clients. Observation file had another problem, another challenge. It was that the observations were encoded inside an element that has an any type. What is described as any type in the XML schema. So some data binding tools are not capable of recognizing the structure, the types of the information that is inside this type. So, for example, Xfinder, one of the tools we use for generating code for mobile, just ignore any tag defined with any tag. Another problem is that within these types, within these any types, usually the observations are packed in a block of observation values that is represented as a string. For example, we can see here, if we generate a parser to process this information, the parser just returns a string. So in the application, to be able to access all the observation values and the rest of the information that is contained here, we have to process all this information again. Well, one of our objectives was to see if it was really true that using a generator, using an XML value to really produce code that was slower than code produced by hand. Here we can see for the PC, the execution times above for a small file and below for large files. We can see here the comparison between the execution time of code that was generated against the code that is written by hand. We have here is just the execution time of the parser. We wrote some test cases where we just parsed the document, but we didn't do any processing out of it. We just wanted to know if what time was needed by the parser to traverse over the XML structure. And we get as results as, for example, DBNG, that is a generator that was developed by ourselves. The overhead that was added to the parsing was not really too much. And the same happens for XML beans, that is a mainstream code generator they use as underlying parser Piccolo, which is a very fast parser. And XML beans do not add too much overhead to the parsing process when converting this information to an object structure inside the applications. On the other hand, in the mobile scenario, while we were processing a small file, was more or less the same, yes. DBNG didn't add too much overhead, but when we try to process a large file, we have this large difference between the time that is spent in parsing the file and this large overhead when we try to convert all this information into objects in our application. The problem here is like when we are rushing to files that have a size of 1 megabyte, the memory of the device is not enough to store all that information. Then, in the case of Android, they have a garbage collector that every time they need memory, they start to execute the garbage collector to try to reclaim as much memory as they could in order to continue storing the data in memory. That's why this difference is because the high frequency in which the garbage collector is executed in the mobile scenario. So this experiment suggests that writing XML processing code using a manual approach do not necessarily produce a code that is much faster than code generated by some tools. That's why my recommendation is, unless you have another problem with this generator, always use the generator, because you can waste a lot of time trying to write the code by hand, and then at the end you can came up with an implementation that it has more or less the same performance. We tried also to measure the memory consumption of the XML data binding tool. We couldn't do it for the mobile. We just did it for the PC, and here we can see that some tools like JAXB or XML bins show higher memory consumption, but here I think you can see the numbers. In this case, when we were processing files of about 3.5 megabytes, they use about 22 megabytes of RAM memory. So, considering the amount of memory that have PC or servers today, it doesn't seem to be a problem for an implementation. Although if we have a server that is expected to have 12 thousands of users, it may be represent some kind of can present some difficulty in the future. We also measure the size of the generated code. In this case, we have all the size of the code generated by all of the two together. But if we should have separated this with X binder. This is code generated for a mobile, starting from the full SOS schemas, and we have a code that is almost 4 megabyte size, and DBMG, that is another tool for mobile, will generate only a code that was below 200 kilobytes. This is why, as I was explaining yesterday, as we knew beforehand the files that we wanted to parse, we just extract from the schemas only the parts that we really needed, and the rest was ignored. So the conclusion for this experiment is that the code generated based on large schemas usually have a large size, that customized code fits better the limitation of mobile devices, and that this customized code does not necessarily have to be written manually. Well, the conclusion is like we have a performance study that is not finished yet. We want to keep measuring some things that we haven't time to do, like memory consumption on the mobile devices, and still try with other tools. And the results suggest that XML processing does not seem to be a bottleneck in PC applications, but the opposite happens in mobile devices, where the time needed to process large XML file is very high due to the limitations in the hardware of these devices. Thank you for your attention.
Thank you.